Assalamu alaikum. Hope everybody will be fine there. Let's move on to the coursework of Plasma Physics 2. Today, well, you can find this topic in the Francis Chan's book in the chapter number 7 and the paragraph number 7.4. All right, we will try to find the dispersion relation of the electron plasma wave. Before, you know very well that in the we have derived this dispersion relation of the electron plasma wave by using the fluid model in the semester 1 of plasma physics 1. So today we will try to derive this dispersion relation of the electron plasma wave by using the kinetic model. I think in my yesterday's lecture I have tried to explain you the kinetic model and the comparison between kinetic and fluid model, and then we have derived the velocity equation. Well, you know that velocity equation or the kinetic theory deals with the macroscopic motions of the particles, and this velocity model or the kinetic model is applicable to the research in the space plasmas, in planetary magnetospheres, in stellar winds, and to the relativistic electromagnetic plasmas either produced in the interaction of ultra intense laser pulses with matter or present in the high energy density environment around compact astrophysical objects. Well, here I have mentioned only few applications of the kinetic or the velocity equation. You can find a lot of applications on the Google search. You know that in the part one of the kinetic theory, we have derived the this velocity equation. I believe all of you understand its derivation. So today we will use this equation to find out the dispersion relation of the electron plasma wave. You know that if we and here is the acceleration, f is the distribution function, alpha are the particles. If, for example, if you want to write down the velocity equation for the electron, then alpha will be E, for the proton will be P, etc. Alpha, in fact, alpha are the plasma particles, U is the velocity of the particles, del you know is the space operator, and partial f by partial U is the change of the distribution function with respect to velocity, and here it's the change of the distribution function with respect to time. Well, if you multiply, here is the expression. If you multiply and divide this acceleration by a force, which I have done over here, then you can see that in the numerator we can have a force. So if we want to find out some electrostatic dispersion relation like we are doing today, so then in that case, this force will be electrostatic force. Generally, you know that force is defined as ma, but for the plasma system, as it is a charge system, so we will be having the electric, magnetic, and the gravitational forces for our consideration. And today we are going to derive the electrostatic mode, which is the electron plasma wave. So force will be the electrostatic force. Yes, here you can see that when a volume element evolves under the effect of force, like in an incompressible fluid, and remain constant. Here you can see that when incompressible systems, the number density and the velocity, this is the perturbed velocity and this is the equilibrium velocity, both are equal. So for which is the case of the incompressible system. And since we are dealing with the electrostatic mode, so the force is the electrostatic force, while as we have in the Lorentz equation. So if we substitute this for instead of F, if we substitute QE, we will be writing this velocity equation for the electrostatic mode. Now to linearize, you know, whenever we have to incorporate the wave into our system, we have to linearize equations. So in order to linearize the velocity equation, we will first of all linearize the distribution function. So f alpha, the total distribution function, will be equal to the equilibrium distribution function plus the perturb or the oscillating distribution function. So if we making use of this distribution function into equation number 9, we can have the linearized or the perturbed velocity equation expressed here. Here u will be the equilibrium velocity, because f alpha 1 is the perturbed distribution function, so otherwise this term will be non-linear term. And here since f alpha naught we have used the equilibrium distribution function, so this e the electric field will be the perturb or the oscillating. And also you know that we can write E as the electrostatic force as minus del phi. So substituting this over here, we have the linearized velocity equation for the electrostatic potential phi 1. I believe all of you will understand well, because mathematics is, of course, it's some lengthy mathematics, but it's not very much complicated. Well, then, making some simple mathematics, we can write the previous equation like here, and taking this to the right hand side, and then applying the Fourier transformation. You know, when the perturbed quantities, on all the perturbed quantities, we can apply the Fourier transformation. I believe all of you know very well. So this is the this equation looks up after applying the Fourier transformation like here. And similarly, um, we can um, we can have the perturb distribution function f alpha 1. From here, we can derive it like this one will be equal to minus q k. K is the propagation vector, q k phi 1. Phi 1 is the perturb electrostatic potential, m is the mass of the particle. For example, if you will be considering the electron, then this will be the distribution function for the electron, then this will be the mass of the electron. Omega is the frequency, k is the wave vector, u is the velocity, and partial f alpha naught is the equilibrium distribution function, variation of the equilibrium distribution function with respect to the velocity. Well, this is the definition of the perturb distribution function in terms of the electrostatic potential. I have named it as an equation number 10. We will make use of this equation later. um, since we are dealing with electrostatic waves, so let's write down the Poisson equation for the charged particles. We suppose that if we have two type of particles, the ions and the electrons into our system, then Poisson equation looks like here, where you know that del is the space operator, E is the electric field, um, E is the charge of the electron, and these are the number density of electron and protons. If we linearize this Poisson equation, we will be right. We can write this expression as del dot E1 is equal to minus 4 pi E n E1. Yes, in the perturbation, we have not taken into account the ions or the proton part, because we are deriving the electron plasma wave, which is the high frequency wave. You know, electron wave or the high frequency wave. So in the high frequency oscillations, ions will not take part in the perturbation or oscillation, and will remain fixed at the background to satisfy the quasi neutrality condition only. So this is the perturb Poisson's equation for the electrons. And you know, generally from the fluid or the kinetic model, I have told you in my initial slides, that we can calculate the number density of any plasma particle if we integrate the distribution function over the velocity space. So here we can calculate, for example, here E1, instead of E1 we can write it as minus del phi 1. So this will make it as del square phi 1 is equal to summation alpha, and here will be 4 pi q alpha, and instead of this number density, we will be writing it as f alpha 1 d cube v, because we know that the number density in the kinetic model we can have by integrating the distribution function over the velocity space. So I have made use of this definition of NE1 in equation number 11 to obtain equation number 12. Well, all right. We are here as a simplicity considering the one-dimensional motion only. So dqv can be simply written as dvx for the x-dimensional motion, and q represents the charge of electron. All right. Then simply yes, if we substitute f alpha 1, which I have derived before, into equation number 1, we will get this linearized equation for the electrostatic potential phi 1 as k square phi 1 equals to summation 4 pi q alpha square over me. The integration will be over uh, uh, partial f alpha naught over partial u dvx, and here omega minus ku. We have to calculate this integral. I'm speaking about this integral to get the dispersion relation of the electron plasma wave. So if we just multiply this equation by n naught e, and just multiply and divide by n naught e. This term will turn into plasma frequency. You know that omega p e square is equal to 4 pi n naught q alpha square over me, and this number density will be left here, which we have divided this expression with the number density. And also we can cut this phi 1 on both sides, and k square as well, to have this expression will be reduced over here. 1 is equal to summation alpha omega pe square over n naught e, in all this combination, partial f alpha naught u by partial u, and dvx because we are considering only the one dimensional motion now. And here is the definition of omega pe square. So we can write this, let's name this equation as the equation number 13. Now we will try to calculate first of all this singularity here, 1 over ku minus omega, and then we will make use of the Maxwellian distribution function. We will differentiate Maxwellian distribution function with respect to u, and then whatever we got we will substitute uh, into this equation number 13. So let's name this as equation number 13 and do the necessary mathematics. Well, all right, the electron dispersion relation, you know that electron plasma waves are high frequency wave, and if only the electric field is present into a system, we will be having the Langmuir wave, omega square is equal to omega p square. You know, all of you know very well, we have derived this dispersion relation in detail. And if the temperature or the thermal motions are also present along with the electric field, then these oscillations or the Langmuir wave will propagate into a wave as shown here, known as the electron plasma wave. And today we will derive the dispersion relation of this electron plasma wave. So here, this is equation number 13. And now, as I told you before, let's try to solve this denominator first. So you know that this omega generally consists of two parts, the omega real and omega imaginary. So I'm just leaving this equation here. I will solve this denominator and then substitute the value back into equation 13. So let's write down 1 over ku minus, because omega consists of both real and imaginary parts. So I'm going to write it here. Then taking ku minus omega r as a common, this expression can be written like this. Or I can multiply. I'm going to multiply and divide this expression by 1 plus iota omega I over ku minus omega r to have this expression. And then simply uh, if you multiply these two combinations, then in the numerator will appear omega I square. And you know that omega I square, the imaginary frequency is always very less than the real frequency, or the omega r is much more than omega real imaginary. So the square of the imaginary term can be ignored here. So this combination we will ignore here. Yes, this is the condition I have mentioned here, that omega real is much more than imaginary omega. So omega iota or imaginary square will be less than 1. So I'm going to neglect that part. So that denominator terms will be simply left with as expressed here. Then let's substitute this value into equation number 13. So equation number 13 will now looks like here in the equation number 14. And if we take k common from here, if we just take omega pe square and the k take common from here to make it k square, and inside the integral will be f partial f alpha naught over partial u dvx, and divided by this combination ku minus omega. All right, here one thing you can note that in equation number 14 I have just taken the real part of equation number 14. I mean, in the real part we will be having 1 minus all this combination, and then 1 divided by this ku minus omega r, and then all this combination, and then have taken k outside. This imaginary part I'm not going to consider now. We will take it into account, this imaginary part, to have the imaginary dispersion relation of the electron plasma wave. But right now we are just deriving the real dispersion relation of the electron plasma wave. So in equation 14 I'm just taking the real part. So this equation 14 in the real part looks like in the equation number 15. Now let's take the denominator of the equation number 14. We will solve this denominator and then substitute back into equation number 15. So this is the denominator of equation number 14. uh, we can do as very simple mathematics and then can take this omega r over k outside. So this denominator now looks like here, or we can rewrite this expression here as now because this one is much more than all these combinations, so we can have the expansion on this equation number a. Here is the general expansion, or if we apply this extension on the equation number a, we will be having minus 1 over 4 omega r over k, and inside we will be having 1 plus u over omega r by k plus u square over omega r over k square, and plus u cube over omega r over k cube, and plus so on. So this is equation number 16, which we will substitute back into equation number 15. So here if we substitute beta in the Maxwellian, if we write down the, actually here is the Maxwellian distribution function. Here down is the simply the Maxwellian distribution function, and if we substitute in the Maxwellian distribution function beta as m over 2 kt, then the distribution, and differentiate the Maxwellian distribution function over the velocity space, we will simply have this expression. You know that this is the coefficient of the Maxwellian distribution function, and if we differentiate the Maxwellian distribution function over velocity space, then do d 2 u beta exponential minus beta u square appear here. And here you can see that, or if we multi here, a partial f alpha naught by partial u can be written as minus n naught m over kte. We just combine these two, uh, m over 2 kt to have it as 3 by 2, and then 1 over square root 2 pi is as it is here, this u is as it is here, and then exponential minus beta u square. Then making use of the equation number this 17 and 16 into back into equation number 15, we will get all this combination which is written here. Again, let me remind that we have substituted equation number 17 and the equation number 16 in my previous slide into equation number 14 to get this final expression. Well, here, yes, here you can see all these combinations are, if we substitute the value of the here, you can see if just we multiply this omega r over k inside the this bracket to have u over omega r by k plus u square over omega r by k square plus u cube by omega r over k cube, and plus so on. So in order to solve this integral, we will make use of this identity integral. You know that generally, I believe all of you know very well this generally identity integral. Here, this integral exists only for the even combinations of n is an integer, 1 2 3 4 could be any, but this integral exists only for the even combinations of n. I mean, n can be 1, n can be, if n will be 1, it will be even, if n will be 2, it will be even, if n will be 3, it will be even, and so on. So this integral only exists for the even combinations, but all the odd combinations vanishes or becomes 0. So I'm just I have written here. So if n is equal to 1, this combination gives us 2 minus 1 factorial over 2 beta and square root beta pi by beta, which is the solution of in our equation number final equation, the u square exponential minus beta u square dv gives you this combination. And then if we substitute n is equal to 2, then here if you substitute n is equal to 2, then obviously this u becomes 4 u4e exponential minus beta u square dv will gives you this here final expression. The mathematics is very simple here, like here. So let's substitute these u square exponential minus beta u square du and u4 exponential minus beta u square dv terms back into our fine equations which we have got before, and assuming all the odd combinations vanishes or becomes 0, so our dispersion relation will finally looks like here. I think believe all these quantities. M is the mass of electron, K is the Boltzmann constant, T is the temperature, K square is the propagation vector. Here, this is the plasma frequency, and beta. In the Maxwellian distribution function, we have named it as m over 2 kt, and these are all two combinations. This is the combination appearing due to u square exponential minus beta u square du, and this is the expression appearing due to u4 terms. Well, if we substitute back beta m, which we have denoted as beta is equal to m over 2 kt here, then our expression will look like this. And then so here mathematics is very simple, I believe. You just substitute the value of this beta here and here, then you just take something, this m over 2 kt here, and this m over sometimes it will cancel out here, like, and this will cancel here, to have finally 1 minus omega pe square over k square. It's 1 over omega r square plus this combination. Let me remind you that we have done nothing. We have just cancelled out this pi here, and then 2's here, and then this combination m over 2 kt outside and inside will some add up to gives you uh, this final expression. Or we can write it as 1 minus omega pe square over k square, and k here you can take this k square up, so this will look as k square over omega r square, and plus here this will look k4 over omega r square, and this combination equals to 0, where you know that v thermal square is defined as 2 kte over mass. Well, finally, we got this dispersion relation of the electron plasma wave. Now, after doing some very simple mathematical steps, we can have the final dispersion relation of electron plasma wave. Here, we have opened this bracket to write this expression like here, minus 3k square v thermal e square over omega r4, and then simply we can write this expression as a biquadratic equation. This is a biquadratic equation where you know that omega lambda, yes, I believe you know that the d by length is defined as the v thermal square over omega pe square. So or v thermal square here can be simply written as lambda de square omega p square. Let's substitute it into equation number 19 to have this quadratic formula. So omega, this is sorry, this is actually a biquadratic formula, so we can apply the quadratic equation to find the roots here. So we just say that a here we just say that this is the biquadratic equation in omega r square roots. Here we just say that a is 1, b is minus omega pe square, and c is all this combination 3 k square omega pe4 lambda de square. So if we apply the yes, here is the quadratic formula. If we apply the quadratic formula, we will get this simply this equation number 20. Now if we apply the binomial expansion here, then this 1 plus, I mean this combination simply looks like here, and by ignoring the higher order terms, we will get this equation number 20 reduces over here. Omega r 2 omega r square is equal to 2 omega p square. Yes, here was 1 plus 6 k square lambda de square, and if we just ignore this 1 in comparison with the k square lambda de square, or if we apply the plasma approximation, we can have this expression here, we are just ignoring. uh, we just if uh, Here you can see that if we add, open this summation bracket, then this omega p square with this omega p square makes it 2 omega p square, and plus all this combination, and then we can cancel obviously 2 on both sides to have this dispersion relation. Then substituting back the value of lambda d square here, which I substituted here, we can get this final dispersion relation of the electron plasma wave. So this is the dispersion relation of the electron plasma wave. I believe you all remember we have derived this dispersion relation before by using the kinetic model, and now we have derived this using the kinetic model before we have derived by using the fluid model. So here we can discuss this dispersion relation as if there are no thermal motion, then this part will disappear and we will be having only the real oscillations. However, in the presence of the thermal effects, in the absence of the thermal effect, you can see that we are only having to and fro motions, oscillations, because there is no propagation. The wave will not propagate, it will just oscillate. However, in the presence of the thermal motion, we can see this propagation vector over here. So the electron plasma wave will be propagating now uh, in this situation. So I hope all of you understand the derivation of the electron plasma wave by using the kinetic model. We will have a discussion if you understand something. If you not be able to understand anything, I will always be there to help you. Good luck with your learning.